Okay.
Have you found the effective mass of the spring?
All right, so the period is 2 pi times the square root of m over k. And from part A, I believe it is, you know what the spring constant is.
Oh, no, I couldn't figure out the spring constant.
Pardon?
I wasn't sure how to find the spring constant.
Oh, all right, so let's start there. I know that, ignoring direction, that the force exerted by the spring is equal to k times delta x. So how far it stretches versus the force. Now, since you put the mass on the spring and it would hang in equilibrium, that means the weight equaled the force from the spring. So mg, therefore, would equal k delta x in our particular situation.
Yeah, I got to there, but wouldn't the mass be the mass of the spring and the mass of the weight? And you don't know the mass of the spring?
What the mass, all right, so let's bring that into it. That actually, no, if you're going to pull k from the slope. So I have a spring here with a mass hanging down on it. And so in essence, I've got mass, I call it mass hanging mass, and then there's the weight of the spring. Acting up, I have the force from the spring. So mhg plus msg is equal to k delta x. Now, you're plotting here delta x versus, I guess, msg. mhg. So let's solve for delta x. So delta x would be, that is sort of my x-axis. That's my horizontal axis right there. That's my vertical axis right there. So I want to get it into slope-intercept form. And so delta x becomes 1 over k times mhg plus msg over k. So that's my variable. That's my variable, horizontal variable. That's my intercept. And that is the slope.
Okay.
So from that, you can figure out what the spring constant is. Now back over here. So when you start oscillating it, it does depend upon the mass, but you have nothing on the spring to begin with. The first time you do the oscillations, there's nothing hanging on it. And so this mass here has to be the effective mass of the spring. Because that's, since you don't have anything additional to it. So this would be the effective mass. The period, you timed it for, what, 10 oscillations? So you can find the period for 1 oscillation. And that was redundant. K you have found already from the previous part. And so you just solve for effective mass.
Okay.
And so now when you add on another mass to it, it'll be the effective mass plus whatever you hung on it. Other questions? Sorry, could have done my caramel.
Can I show you? Because I'm confused.
Right.
So, from part A, I think it says average position of
Right.
the loose coil
Yes.
versus hanging mass. So, the gradient is, I think, G over K.
Oh, yeah, okay. So instead of doing it against the weight, I said do it against the mass?
Yeah.
All right, so that puts G over there.
So then, that's my gradient, and then for, he said mg is equal to whatever this is. I think this one was for 0 kg, so I put it there, and then mass is equal to that divided by that. So then I just, for this, to find the effective mass of the slinky, I did 1 over slope, 0.1 times 1 over slope.
Wait, to find the effective mass, you did 1 over the slope?
No, it's 0.1, like the extension for 0 kg. So I use this formula, mg equals k delta x, and delta x was 0.1. And then I got mass equals 0.1 k over g. And then since I got from here, it's g
Sorry,
over k.
that 10 centimeters comes from,
When there's no mass hanging.
that's just the natural hanging length?
Yeah.
So it hasn't, that doesn't really count as the stretch?
So what?
Unless you're doing a comparison between, the slinky like this and the slinky when it's hanging.
Well, I guess what I did was this minus this.
Okay, so the position, so
for 0 kilograms.
but it wasn't in equilibrium when you pulled it down to there.
Oh, then I'm confused.
All right, so I was suggesting you find the effective mass from the period when you had nothing on it, as opposed to potentially what you have.
But I
K,
had
you
nothing
could solve for
on
the
it.
effective mass.
But I had nothing on it. It was 0 kilograms. There was nothing. It was the data for the 0 kilograms.
Right. But the data, you're talking about this hanging mass.
Yeah.
Or sorry, you just took a slinky, you had some set of coils and you just let it hang. That's the data point that you picked, right?
Can you repeat that?
So when you did not add anything to the slinky, all you had were a bunch of loose coils hanging down.
Mm-hmm.
You're saying that distance right there was 0.1.
No, that distance was 0.151. And then that's for the first part, and then for B, I think we
You
stretched
pulled it down.
Yeah, we pulled it down, and then we measured the oscillations.
Right.
And then, so what I did was so when we pulled it down 10 centimeters.
Right.
So that's where the 0.1 came from.
All right, so if you want to look at that information right there, when you pull it down to this point and let go, it doesn't hang there when you do that. As soon as you let go, the thing starts moving upwards. It accelerates.
Mm-hmm.
So at that point right there, we have K delta X acting up, where delta X is how far you pulled it. We have, I guess, effective mass times G acting down. And so we have K delta X minus mg is equal to ma. So right off the bat, you were setting it up with like an equilibrium equation. You basically set those two things equal to each other when they're not.
Okay, so I don't understand what you were suggesting earlier. Because how do we have the time period when we don't oscillate it?
So this right here was from part A, when it
Yeah.
wasn't oscillating.
Yeah.
It was not. So the main point of my having you do that was to be able to find the value of the spring constant.
Yeah.
All right. Now you come to part B, you were oscillating it with no additional mass on it. And ideally, if there's no mass, if I take something with no mass, I stretch it and let go, that thing should be moving infinitely fast,
Mm-hmm.
because the period would be 0. But obviously it takes time.
Yeah.
I feel like I'm not addressing your concern.
So how do you find the spring constant again?
All right, so once you have delta x for the mass and not the weight as
So
I.
this is the graph from part A.
Yes,
Okay.
you're gonna have a set of data points.
Yeah.
You'll do a trend line. This is your y is equal to the slope x plus b,
Yeah.
slope intercept form. And so I take the slope of that, set it equal to g over k.
Okay.
That makes sense.
I get it now, I think.
All right.
Wait, so for the first graph, is it G over K or is it 1 over K?
If I had forgotten what I
It
asked
says,
a lot.
Average position versus hanging mass.
Hanging mass. So I plotted mass and not weight as I originally wrote down here. So where I did have a g here, I just moved the g up front. So the slope is g over k.
Then from that we can find K.
Yes.
Yes.
And once you have k, you assume you've done it correctly. You can plug that into part B. The period when you have not added anything additional to the slinky, that'll get you effective mass.
So how do we find the effective mass of the slinky?
All right, so has anybody found the spring constant yet? Okay. I'll make up a number. So let's say that K was 10 newtons per meter. You take the slinky, you pulled it down 10 centimeters and let go. Now it's oscillating back and forth. You time how long it takes to take 10 oscillations. And so if 10 oscillations took 20 seconds, that means the period 20 seconds over 10 oscillations. The period was 2 seconds per oscillation. So now we come to our period the equation for the period. So we'll have 2 equals 2 pi times the square root of m over 10 newtons per meter, our value for k. Solve for m. Solve for that m. That m is meters. It should be somewhere around 1, math-wise. Sorry, 1 based upon the numbers I used here, not based upon what you have. I would be surprised if the mass of your slinky, effective mass of your slinky was on the order of 1 kilogram.
How do we find the amplitude?
The amplitude, so it has some natural length to it. That's when you just put the mass on it and you let it sit there. You pull it down to a certain, to some new spot, and so the amplitude is just the difference.
So if you brought it down 10 centimeters, the amplitude would be 10?
Yes.
Okay.
Okay.
Other questions? Okay. All right, so what we're trying to do is try to figure out where is the speed the fastest as we pull this thing. So we had it to here. I assume, that's right. We found out K based upon what we had done before. And so then we pulled it down. How far did we pull it down? So it's actually K 3 meters, and then we pulled it down additional 7. All right. And then let go. And I'm assuming that's probably just before this equation got written down, so.
9 Yep.
That's 4.9 or 49?
It says 4.9.
4.9?
Yeah. That looks right.
All right. So we're trying to figure out at what point is the speed the greatest, and so we did a conservation of energy here, knowing that the spring was stretched 10 meters when I let go. So V is equal to the square root of all that, so we're just going to all that to the 1/2 power. And the question, I believe, was, how do we actually find the maximum speed? My recollection is it was met by silence. But now you've had time to think about it. Also, I think I revealed it at the end. But how do you find speed, our maximum speed?
Wasn't the derivative?
It's a classic max min. Since we're trying to find the position where the speed is at a maximum, we find dv dx. Set it equal to 0. So I have 1/2 times all of that. It might be helpful. What is that? So while that's being revealed, plus 29.4x over 1.5 minus 4.9x squared over 1.5 to the negative 1/2 times.
Wouldn't it be 0 though?
Pardon?
If you take the derivative, wouldn't it be 0 since it's a constant?
Because I have the square root here, I have to take the square root of this whole, of
Oh, yeah.
that first, and then the square root of what's inside. Then that's when the 0 pops in. What? I guess.
got negative 490 over 3. Did you guys get that?
Negative what?
490
4
over 3.
over 3. So I have this whole thing set equal to 0 if I just multiply by my denominator to the negative 1/2, so it's in the denominator. Matter of fact, I multiply everything by this square root and 2, and I get rid of all of that. So what I'm left with is, or let me write that out a little bit. So I have 29.4 over 1.5 minus 9.8x over 1.5 divided by 2 times the square root of all of that. Equals 0. Now the math people tell me that a fraction is equal to 0 if the numerator is equal to 0, so let's go ahead and trust them this time. So I have 29.4 over 1.5 minus 9.8x over 1.5 is equal to 0. Then I can just multiply times 1.5. So 29.4 minus 9.8x equals 0. X equals units. Solving for the position when the speed is the maximum. Meters, yeah. In other words, the maximum speed occurs right there in equilibrium. Which was the exact same result we had when we had this thing horizontal and I pulled it out and let go. Its maximum speed happened when it was at equilibrium. It's as if the gravitational potential energy had no effect whatsoever, at least in answering this problem. So let's do it slightly more generically. When you are given the vertical problem, you can, and you're looking at energy to figure out what the maximum speed is, you can do it exactly the way we did it here. Bringing in the two potential energies here, we had the kinetic energy plus the potential energy from the spring plus the gravitational potential energy, which is exactly how we got to this point, where this is the point where x is equal to 0. Or you can ignore the potential energy and just treat this as x is equal to 0. And you get to the exact same place. Questions? And I know I took a specific case and just generalized it, but if you want, we can go through the derivation in more general terms, but we'll get to the exact same place.
So you find the maximum speed by substituting x into the equation, right?
What we did was we had 1/2 mv initial squared plus 1/2 k x initial squared plus mg h initial equals 1/2 mv final squared plus 1/2 k x final squared plus mg h final. I mean, what we did here was we started with it at its maximum stretch there. I think that's where we made h is equal to 0. Then x was 10 meters. Vi was 0 because that's where we started it. And then we solve for v, this v right here. Or we could have just treated this as x is equal to 0 and ignored u sub g. Somehow I think I missed your question. You want to try it again?
Yeah. So we got the position at which the thing is at its maximum speed.
Speed, yes.
Is 3 meters.
Yes.
So if you substitute 3 meters into that equation, the v squared equation, you get v squared max.
Yes.
But when I do that, it's giving me a negative, so how can I square root?
We have a sign off. Let's see. We did set h equal to 0 at the bottom. Is that? And so I know that h is this distance, x is that, so x plus h is equal to the amplitude, or 10. So h is equal to 10 minus x. That was 0. This becomes 1/2 times 9.8 times 100 plus, well, that's the total energy, equals it was a 3 kilogram mass, so there's the 1.5 v squared plus 1/2 kx squared plus mg 10 minus x. So when it's there, x is 3, h is 7. So that holds over there. I'm just making sure I don't have a minus sign in the wrong spot. At this point right here, h is 10, x is 0 here, x is 10, h is 0. Yeah, so I'm still good with x plus h equals 10. So that's 49 plus 1.5 v squared plus 4.9 x squared plus, this is 29.4, so that becomes 294 minus 29.4x. That goes over, that goes over, that goes over. Huh. Oh. Shame on all of us. 490. All right, now you put your 3 in.
I got 12.65 meters per second.
Which should be the same answer we
Yeah.
got when we had it horizontal.
Yeah.
Okay, there we go. Thanks for pointing that out. Ah, well. The only way not to make mistakes in physics is not to do it. All right, any other questions? All right, so we've established simple harmonic motion, the fact that if something is in simple harmonic motion, in other words, that the force acting on it obeys Hooke's law, then we get simple harmonic motion, and whether it's horizontal or vertical, we can still use the same rules there. So let's take a look at a situation where does it obey Hooke's law? What we will call the simple pendulum. So I'm about to erase this.
So we did everything right to get the distance, right? The place where it's at max speed, we did that right.
That maximum, the position of the maximum speed, that still holds, because the part that we messed up on, or that I messed up on,
Constant.
was the constant that derived out.
Right.
Yeah, if we had not gotten 3 meters, I would have noticed a mistake sooner.
That makes kind of sense, because you let go up, then the how you say that, the gravity is much is bigger than whatever the string is not doing anything when you just release it.
Right.
When it gets to equilibrium, they are just compensated, but it still is going down, but now the strings start pulling up somehow. No. Then it's obvious that that's the maximum speed. I mean,
Right, and the fact that force due to gravity is constant throughout also allows it to happen, allows us to be able to simplify it. All right, simple pendulum. All right, a couple rules for the simple pendulum is that all the mass is right there. This is all the mass at a point. No friction at the top. So we pull back to some angle theta, we let go, and it goes swinging back and forth. So with the analysis of almost any problem we do, force diagram, start us out. What are the forces acting on the bob?
We,
Tension.
Anything else?
Did you release from rest?
Pardon?
Did you release it from rest?
Yes.
That's all.
Okay. If I hadn't released it from rest?
Then there'll be a force applied at an angle, I guess, or, yeah.
Oh, from the hand?
Yeah.
Generally, we're talking about even if I released it while it was still moving, once my hand gets off of it, then the force diagram still looks like this. And this angle right here is theta. Now this thing is going to be oscillating back and forth. We do have 2 types of acceleration going on here, connecting it back to chapters 3 and 12. I know it's going to move in that direction there. We have a centripetal acceleration acting towards the pivot point there, and we have a tangential acceleration acting in the same direction as the velocity. So I'm going to set up my coordinate system like that. I'll just call that I and J. So what is, I guess, decomposition time? What do I have to break up?
Weight.
Yep. And so I have weight acting down, and I'm breaking it up into the perpendicular components. Let's see, I know that that angle is theta right there, so this angle right here must be theta. In other words, that angle there, theta. And so this becomes weight times the sine of theta, and weight times the cosine of theta. Redrawing my force diagram there, except with the components, I have my tension acting this way. I have W cosine theta acting opposite the tension, and W sine theta acting in the direction of the tangential acceleration. What are my equations of motion?
J had to just have W sine theta is equal to MA.
Put a little a sub t there, just emphasizes the tangential. And what's the other one?
FT minus W cosine theta is equal to MAC.
Now the second equation we actually don't need for this particular derivation that we're doing right here, just the first one. And so this is here just for completeness. Substitution. I have mg sine theta is equal to m a sub t. Now we do have to make an adjustment here. What is the direction of the acceleration?
Wait, which one?
Of tangential acceleration.
The J hat direction.
What's the direction of the angle? Bringing the rotational stuff in there. What is the direction of the angle?
Towards the forward. Yeah, negative, yeah.
Yeah, because it's been rotated that way. So we have a slight complication here. So we still need to bring in the minus sign, but let's make one other substitution, then we'll bring the minus sign in properly. When you're dealing with it, I know that V is equal to omega r. A is equal to alpha r. This is the tangential acceleration is equal to the angular acceleration times the radius. So if I make that substitution, I have mg sine theta is equal to m alpha r. And now it's a lot clearer that when this thing starts accelerating, it's going to be accelerating out of the board, but the angle is into the board. We need a negative sign there, because theta and alpha are in opposite directions.
Can you repeat how you got the negative sign?
All right. So 0 degrees is, or 0 radians is straight down. So when I pull it out that way, I'm increasing my, so that's the direction in which I'm making the angle. Using the right-hand rule, the vector would be towards, into the board. When it starts to move, the angular acceleration is in that direction, or out of the board. So my angle and the angle and the angular acceleration are in opposite directions. Now, does this obey Hooke's law? Remember when we were first developing Hooke's law, we had the spring force is equal to negative k delta x, or I'm just simplifying to x, is equal to ma. I had position and its second derivative on opposite sides, and I have a negative sign in there. I don't quite have that here. I don't have position or angle and its second derivative. So it's not quite Hooke's law. However, we can get it close. The small angle approximation. So have we done this yet? Small angle approximation, or is this the first time? For us? First time? Small angle approximation says that if theta is much less than 1, then the sine of theta is approximately equal to theta, which is approximately equal to the tangent of theta. Have any of you seen the long polynomial expansion of sine? How to write sine of a function or cosine of a function in terms of like theta squared, theta cubed, and so forth? Sine of theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on. If you take the derivative of that, you should get cosine of theta. Take the derivative with respect to theta. So you get 1 minus, well, multiply times, bring the 3 down front, which cancels out with my 3 factorial, and I'm left with theta squared over 2 factorial, plus theta to the 4th over 4 factorial, minus theta to the 6th over 6 factorial, and so on. It might be Calc 3, I can't remember when. Or differential equations.
Different series.
It is, it's the Taylor series or Maclaurin series. Any of those ring a bell? Okay. At some point later on in math, you'll come across Taylor series or Maclaurin series, and you go, shh, we did that a long time ago. So if theta is small, recognize we have some small number cubed, which makes this even smaller. In other words, all these terms drop off, and you're left with just sine theta is equal to theta. Cosine, if theta is really small, then cosine is roughly equal to 1. Or taking it slightly more sophisticated, theta squared over 2 factorial, or 1/2 theta squared. Now, how close is this? How legitimate is this approximation? And so I have a graph right here. Conveniently, what are the odds? All right, so I'm hoping all of you have eagle eyes and you can see the 3 different lines there. We have the blue one on top. That is tangent. The red one in the middle is just the theta, and the green one is sine. So notice that they are overlapping quite a bit, quite nicely, up to a certain point, at which point they then start to diverge. So as long as we're dealing with an angle sort of in this region right here, it's a pretty decent approximation. Now let's take it one step further in terms of how legitimate is this. These are 10% off at an angle of 0.693978838. Somewhere around 44 degrees. Now in physics, typically if you're at a 44 degree angle, you don't use the small angle approximation. Typically, as long as theta is much less than 1, usually a 10% rule there. So if theta is 0.1 radians, which is about 5 degrees, you're good. But you can expand it a little bit farther. So if the angle is small, then this becomes mg theta. So again, if theta is small, is equal to negative m r alpha. And so now I have some function whose second derivative is on the other side, and I got a negative sign stuck in there. Compare that to what we had over there, where I had kx is equal to negative ma. Well, mass cancels out on that equation right there. So if I'm looking at the parallel there, we've already solved this one right here. This is x is equal to some amplitude times the cosine of omega t, where omega is the square root of k over m. We did that last Tuesday. If we parallel it, instead of k we have g, instead of m we have r, we have r, which is basically the radius here. It is this length, that's r. And so omega up here now becomes the square root of, instead of k, I have g, instead of r, I have l, or instead of mass, I have length. So if I take a simple pendulum and I just let it swing, I have its angular frequency. The period, which is 2 pi for here, the period, which is 2 pi square root of m over k, now becomes t is equal to the square root of L over G. And we're about to exploit that. So I need some sort of pendulum with not much mass in the length of it, and most of the mass hanging at the end. And so I'm just going to take a piece of string, longer than that is preferred, and I need something which is significantly more mass than the string has. Now, this discovery, this derivation, is actually of incredible significance historically. Galileo is the one who gets credit for this. Supposedly, he was in church watching the chandelier swing. Hopefully, I'm not going to swing it so it bangs into the bar. If it does, then we'll go to plan B. So what I'm going to do is I'm going to pull it back, and if you've got your phone or easy access to a timer to the hundredths of a second, pull that out so that we'll get a group on the timing here. We're going to time how long it takes to take, let's go for 10 oscillations. So when I'm ready to go, I'm going to go 3, 2, 1, go. When I said go, I'm going to let go of it, and then we'll count to 10. Just a small angle. All right. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so what times do we have?
16.22. 16.15.
16.35.
16.23.
16.32.
Anyone else?
16.21.
The next time grouping. I'm figuring anyone who did not speak either did not time or they had something so incredibly bizarre compared to the rest of them that they decided to stay quiet. All right, so our average.
16.25.
You got confirmation? All right, and so my period is 1.625, because remember that's the time for 10 oscillations. So we have 1.625 seconds is my time. My length here is from the pivot point. Now the pivot point's not the middle here. The pivot point is where the knot is, because I was looking at that, and the knot basically is standing still. So I'm going to do it from the knot to the middle of this mass, assuming that the center of mass is at the middle there. So we just need to grab a meter stick. And I guess, Precious, you have the best angle there. Is that basically in the middle down here?
Put it up. Yeah.
There?
Yeah, that's fine.
And I'm looking at 67.4. So my length, 674.674 meters. And so let's figure out what the acceleration due to gravity is here, using our somewhere in between crude and good experiment. So we have 1.625 equals 2 pi times the square root of 0.674 divided by g. Whenever I do this, I always have there's that moment of thinking, oh man, this is going to work out. We're going to get 9.798. It's going to be beautiful, and I'll have witnesses, and then it'll just probably end up being 25.
I've got 10.08.
I got 9.67.
Or is it the same thing?
You had 9.67 also?
I did.
Yeah, I got 9.67 too.
Awesome, looks like they're putting you down.
I guess so, huh?
Redeem yourself here, Austin. Units?
Meters per second squared.
All right. Now let's find out how close we actually were. What should the period have been, given our information right there? So, what would the period have been in a nice ideal situation here? So, still 0.674 divided by 9.798, and that is meters and meters per second squared. We will find out if somebody has bragging rights in their timing abilities.
I'm also getting 10.08.
Yeah,
You still getting 10.08?
yeah. I just ran through it on paper too.
Be faster than I can get my calculator. I'm getting 10.08. Austin, I apologize for having thought you were wrong.
Apologies accepted.
Of course, now it's 3 against 3. I pulled I know I did it right. Routine. Yeah, and 100 times 4.9 is only 49. It's somewhere around there. When you work it out, when you rewrite your notes, you'll figure out what the right answer is. All right, so what should the period have been, assuming that everything had been done, if we'd gotten the value that I claim is the acceleration due to gravity?
16.48.
And thus is the nature of physics. To do it properly, though, we would have done various different lengths and come up with a graph. It would have been beautiful, and no doubt, excellent results. What was that?
I was only less than, I was 100 votes second off. I got 16.47.
Waiting for someone else to chime in. Well, I had 16.48, but I just didn't want to brag. All right. We don't have to answer this now, but I am curious about why you didn't say anything earlier. So,
I was like doing the math, and I'm normally late on a stopwatch anyway, so I figured I was late.
okay. I guess that teaches you not to question yourself. Assume everyone else is wrong.
Learned a valuable lesson in that.
All right.
I know.
Yes, Roberto.
This something cannot be, because you got a period of 16 with very close numbers of the other one that was 1.6.
Sorry?
See, is it, we got the same equation that's there to the right, no?
Yes.
Yeah, then, and it's 0.674 on the top in the numerator. Then it's slightly different from 10 to 9, whatever. And how can be 10 times the result. There's something.
Oh.
Okay.
Thank you. I will say that, I've made obviously a number of mistakes. I've had classes where they would just go in, no, that's wrong, I didn't get that. This group tends to be more of the, I don't see, how'd you get that? Not that anyone who's watching this video hundreds of years from now will know who's in this class, but it was a good group. All right. So the power of this, why this is important. We now have a way of timing. Now this was 1.625 seconds, which means that if this time is 0, that's half the period. From here to here is a quarter of the period. We now have a way of timing at least to, well, I can make it shorter. If I make the period 1 second, then I can now do measurements to the quarter of a second. Before that, you had probably drip clocks. I don't think they had, I don't know, what point did they have sophisticated clocks with? I mean, even the first sophisticated clocks probably were at best to the nearest second. But we have a way of starting to measure time in fractions of a second.
So has there been any major theories and laws that have been changed over time because of advances in technology? Just say clocks and
it's a fine tuning that's definitely happened. I even hesitate to say that. With advances in technology, we can start to do high energy experiments. With high energy experiments, you start to notice that, well, actually before that too, you start to notice that some of the classical rules don't apply. And so quantum physics, some of the rules of quantum physics just don't work in, let's try that again. For example, if you're looking at the spectrum, if you look at a particular gas in a light and you can see the light bands that are coming off of it, and they're very specific bands, and classical physics doesn't predict that, quantum mechanics does. So when you get to the level of precision where you can start to look at those things, then you can start to go, wait a second, why does this work? And that branches off into quantum, and then special relativity, measuring things near the speed of light, we just couldn't do that before. So that sort of opens up to, wait a second, something's a little bit off here. Let's do, technology improves, higher precision experiments, and suddenly you realize, okay, that's not some standard error with the equipment, there's something definitely different here.
So Newtonian mechanics is false?
Say it again?
Newtonian mechanics is false.
Newtonian mechanics is an approximation when you're dealing with things that are, in essence, visible to the naked eye and traveling much slower than the speed of light.
So in your reference frame only?
For the most part, I mean, then it comes to the question of at what point do you have to start bringing in the other stuff. In high energy physics, typically the 10% rule again, if you're within 10% of the speed of light, if you're going faster than 10% of the speed of light, that's when you generally bring relativistic effects into it. With quantum mechanics, when you start getting down to I guess things on the size of an atom, that's when those things start to show up.
So they behave differently. Were they always behaving that way?
They're always, well, such a simple question and such a complex answer. One view is that they always behave that way, it's just that it's happening at a level that we just can't observe. Now there is the effect of observing it does affect how it behaves, so that's why it can get into the complicated side of it. I delve into some of this at the end of the second semester course.
Interesting.
I remember there is a beautiful way to develop the equations of Einstein in series. And the first term that don't have any speed, I think the second term is like a speed of the object squared divided by c squared, the speed of the light, and then v3, c3, and like that. But just the second term, if it's in the hour speed here, is so small that we cannot measure it. And the first term is the equations of Newton. Then in our world, Newton is a huge approximation, it's a beautiful model.
Yeah, I mean, the part of what he's referring to is that there's this factor called gamma, which is 1 over 1 minus the speed of an object over the speed of light squared. And so this is one of those things. So the speed of light is 300 million meters a second. And what's the fastest you've ever gone in a car? We'll just exaggerate it, 200 meters a second, which is really fast. So it's small in comparison. And so this factor, which affects length measurements and it affects time itself, this term is so incredibly tiny, and then you square it. So the Newtonian effects aren't noticed. The relativistic effects are not noticed. However, there is one area where relativistic effects do actually matter for something that is not traveling near the speed of light, and that is GPS satellites. If you ignore relativistic effects, GPS satellites get off by 20 feet a day. And so over time, it gets worse and worse, obviously. Although at some point it circles the world, but you get back to where you started. All right, any other questions at the moment? All right, so sort of take it to the next step. Oh, by the way, while I'm thinking about it, so we have obviously today, we have a lab on Thursday. That will end up being the last lab that we do. We have class next Tuesday, and then we won't see each other again until January, somewhere between January and the end of time.
What do you mean?
We don't meet face-to-face after Thanksgiving.
I forgot that.
Yeah, so I think I mentioned this before, just want to emphasize it again. During this class time on Tuesdays and Thursdays after Thanksgiving, I guess we officially have 3 more classes after Thanksgiving, I will be on Blackboard under Collaborate. I created the link. I think I sent out the email or the announcement. So if you have questions, you can talk to me. I should be there. The only exception, there was one class this semester where I was scheduled to meet a group on Collaborate, and I actually fell asleep. I slept for 3 hours that afternoon. I needed the sleep, however, they weren't particularly happy, and understandably. Max?
So, are we gonna have class at this time, or are you gonna make a video?
There are videos galore, and you can watch some of the other ones. There's 600 videos. No, it'll be posted videos to watch.
Okay.
And a lot of it's covering the stuff that we're doing right now. We're ahead of where I usually am with 251. But I'm not doing a Zoom class, if that's sort of where you were thinking.
Wait, so I'm confused. You're saying you'll be there and we can just pop up and ask you questions?
Yes.
But no class?
Right.
Okay.
I'm not taking roll.
So simple harmonic motion is the last topic for this semester?
No, waves in general is the last topic. We have simple harmonic motion we're doing here, and now we're about to branch into sort of more generalized wave stuff, and then we'll get into sound. So that's sort of the last stuff.
So after Thanksgiving, there's technically no assignments due until the test,
What does Master say?
or that's due on the Tuesday that we do the last.
Master set 12 and 13 are due on December 1st.
Okay.
Did we just email this to you?
Yeah,
Yep.
which game?
If you look in the syllabus, there's a section for submitting online. I recommend that you read that. And I also want to emphasize an issue that some people run into when they say, you never answered my question. Once it becomes an online class, if you're asking me a question, please put the word question in the subject line. Because I've seen people submit it and they'll say something like master set 11, and I'm going, oh, they've just submitted it. So I drag it over and I put it in with their other master set 11 stuff. And then as I'm grading it, I go, oh, they actually had a question, but they never actually said they had a question in the subject line. So with this group, if you sent me something that said master set 11, I'm going, oh, that's unusual because they handed in. So I look at it. But once it's online, please make sure the word question shows up in the subject line, if you have a question.
So for the last lab that we're gonna do on Thursday, when do we give that to?
You will, this is when you will use the spreadsheet that, I guess you're not used to that yet. So some of you have been using it, some of you have not. There's going to be an Excel spreadsheet, Excel spreadsheet that you will populate with the stuff that usually goes to the tables, all the numeric stuff that goes into the tables. Then you will submit the analysis. Some people put it in Excel, but usually they do it in a separate document. Some people print it out and just write the answer in where you normally would answer it, and then they take a picture or scan it or somehow digitize it and send that to me along with the spreadsheet.
That is due the Thursday after the lab.
Yes.
The last lab.
Well, it'll actually be because the Thursday after the lab is Thanksgiving.
Oh, all right.
Now, if you want an excuse on Thanksgiving, feel free to go, listen, I got this lab to do. That bastard. Leave made us do this. So anyway. When I was doing IT consulting, I had to take some time off in order to go to the dog and pony show at my kid's school. And I really didn't want to go. So I half jokingly said when I was still with the team, I said, hey, somebody call me on Friday morning and say that there was an emergency that I have to deal with just so I don't have to go. So I'm at the dog and pony show waiting for it to begin, and I get a call from my boss saying, hey, I need you to do something. And I was not sure whether she took me seriously and was giving me a way out or whether there really was an emergency. So I said, I'm sorry, I can't do it. Why didn't you call me an hour earlier?
So are the videos you're gonna post for us to watch after Thanksgiving, are they like class sessions or are they?
No, they are, some of them are me in front of a board and some of them are you get to see my hand in a piece of paper.
Okay.
They are if you've ever seen any of my non-classroom videos, the quality has, over the past 5 years or so, the quality has improved slightly. Why don't we take a small little break here? We'll reconvene in about 5. So let's talk about waves. The two major types of waves that we will deal with here are transverse waves and longitudinal waves. There's a third type of, these are mechanical waves, by the way, mechanical waves. There's a third type of mechanical wave that sometimes shows up in a textbook. I don't think yours does, but I'm just going to parenthetically put a surface wave here. And a surface wave is just basically a combination of transverse and longitudinal. And so that's pretty much close as we're going to get to that one. I might make one other comment in a moment. And then there's another type of wave that is not a mechanical wave at all, that's an electromagnetic wave, and that is something that we cover in the second semester course. So when we talk about mechanical waves, we're talking about something that is physically, a particle physically has to move in order for a wave to propagate.
What is that second word saying? Longitude?
Didn't, that's one word.
Oh, longitudinal.
There are a lot of similarities between the longitudinal and transverse waves, but there are some very distinct differences, so let's talk a little bit about what they are. In a transverse wave, particles in the medium being whatever the material is that the wave is traveling, through which the wave is traveling, particles in the medium move perpendicular to the wave. An example. Let's see if I can make that a little bit longer. All right, I'm basically sending a pulse down that way. The particles in this actually are, in other words, the coils themselves are actually moving this way as the wave moves that way. Perhaps a better example, considering the class, is we're going to do the sports fan wave. We're going to start over here. You two just stand up and then down. As soon as they start up and down, then you do it, and then so forth that way.
2, 1, go.
So the wave was traveling in that direction, but you, the particles, were just traveling up and down. So you're moving perpendicular to the wave. Longitudinal wave, some of you probably can guess already. Particles in the medium. And that is nicely exemplified by the slinky. Actually, I've been demonstrating a longitudinal wave since the beginning of the semester, but you might not have recognized it as such. So I have a wave right here, or I have a medium right here. I'm just going to release some coils. And potentially what you saw was something seemed to travel all the way down to the bottom and to the top. I'll do it one more time just in case you missed it. Let calm just a little bit. And again, I'm just going to release some coils at the top. Did it look like something fell all the way down and then sort of came back? In reality, all that you were seeing was at some points the coils were closer to each other and at some points the coils were farther away. But the wave, the pulse, went down and back up. The coils just moved just a little bit down, a little bit back up. So that is a longitudinal wave. In a surface wave, the particles in the ideal surface wave, the particle basically travels in a circle. And if you've been to the beach, if you've ever gotten caught in a wave, you feel, you get pulled one way and then sort of you get pulled back. That's in essence what's going on there. The ideal is a circle, but it, in reality, is probably, one of those things physicists go, close enough for us. So some examples of these. I'll stick with red. Longitudinal wave, sound wave. Sound is a longitudinal wave. That's why I said I've been demonstrating a longitudinal wave since the beginning of the semester. Sound. Transverse wave. We have basically pulse in a coil, pulse in long coil. And here we have pulse in slinky. In geology, transverse waves. Let's see, so longitudinal wave, we have the P wave, and then transverse, we have the S wave. And this brings up a key difference between the two. In a longitudinal wave, the reason sound is a longitudinal wave is basically my vocal cords are vibrating back and forth. They are pushing air molecules out in one direction, and then when my vocal cord snaps back, there's a little bit of pocket of what's called rarefied air. But the particles that get pushed forward hit other particles, which hit other particles, which hit other particles. And so the wave is produced outwards by one particle hitting another one, hitting another one. Transverse waves as my hand moves up, the speed of the wave depends upon how much this coil is pulling on the coil next to it. So if you are dealing with a solid, if I lift up this end of the table, well, the rest of the table reacts to it. But gases, it's a little bit harder. So I'm going to move air molecules in front of me and see how well you feel them. Other than Jesse, who's very sensitive. Air molecules, when air molecule gets pulled this way, it's not necessarily dragging the next one along with it. And so, earthquake occurs here. It sends shock waves through the earth, and here you've got your seismograph. That's the seismograph that my wife worked with and I helped her. And it's going to measure the two types of waves, because both are produced. However, the longitudinal waves get there first. The transverse waves don't. And this is one of the key pieces of evidence that the core is not solid. Because a transverse wave will hit, longitudinal wave will hit, and that pulse gets sent all the way through to the earth, through the earth. So what's inside here obviously can transmit longitudinal waves. The S waves, the transverse waves, when they get to here, they basically stop. So they have to go around the long way. So in terms of what do S and P stand for, I haven't gotten a clear answer on this one, but it could stand for two things. The P could stand for primary because it gets there first, or it could stand for pressure, because you have one thing bumping into another. Whereas S waves stands for either secondary or shear. And shear is if, we can demonstrate shear with this linking, because what can't you do with this linking? I apply a force at the top and it sort of shears off to the side. That's an example of a shear force.
So longitudinal waves can travel through vacuum.
Neither can travel through a vacuum. None, mechanical waves
both
can.
of them. Oh yeah.
Because they require a medium and the vacuum doesn't have a medium. These, on the other hand, do. However, if you look historically, and some of this we'll cover next semester, because it was thought all waves have to travel through a medium, that's why they sort of made up this medium in outer space, because they had to figure out how do these waves get from the sun to us, and so they made up this thing called ether. This is not the gas that they used to use for knocking people out for surgery. It's ether as an ethereal. And then later realized that the ether does not seem to exist.
So wait, what's stopping the waves that are going around the side?
The transverse waves require, as one particle moves, it drags the next one with it.
Okay.
And when you get into the core here, which is not solid, a particle moves like this, it's not dragging the next one with it, and so the wave basically dies.
Gotcha.
And presumably, again, the only geology I know is what I've picked up on the streets and from my wife. So, those days in the gang talking geology. So they take into account the distance. It's obviously traveling a greater distance. So when they're trying to figure out how long does it take the wave to get there, or how fast it's traveling. And then with a bunch of complicated calculations, you can start to figure out the thickness of the crust here, and presumably some of the makeup inside here. Or it's geology, so they'll just use a Ouija board. Any geology people in here? Future geologists? Any objection if I just insult geology people? And I know perfectly well my wife could possibly watch this video, so yes, I haven't made fun of subparallel yet, just so you know. All right, so when we're talking about representing a wave, I drew lines right here, but what exactly does that mean? So let's talk about a little bit about the two waves and how I represent them physically. So let's just take sound for example. Sound is a series of pressure, of of compression and rarefaction. So I get a bunch of air molecules. And as a side note, I know that air is not a molecule. Air is composed of a lot of different molecules, but I'm still going to use the term. All right, so I have a bunch of air molecules here, all bunched together, and then I have these places where there's fewer air molecules, and then I got a bunch of air molecules sort of compressed. This is when the vocal cord snaps one way, and then when it snaps back, you get this rarefied section, and then fewer, and then high pressure again. So this is compression and rarefaction. I've always heard it pronounced with the two syllables there, not just rarefaction, but rarefaction. Faction, not fraction. Now, it is not convenient writing on the board, writing a sound wave like that. Another way that I could write the sound wave is I could do it sort of like this, where these lines represent high pressure, or the highest compression. So this would represent sort of the middle of the compression, and in the middle here would represent the rarefaction. The third way that I can represent it is basically with what looks like a sine or cosine curve, which is really convenient, where I've got the high pressure, low, high, low, high. So all three of these can represent a longitudinal wave. If we're talking transverse waves, this could actually physically represent what's happening in a transverse wave. That when I take the coil and I put a wave in it, it physically looks like that. For most of what I'm going to be doing, I'm going to represent it this way. When it gets to the Doppler effect, I'm going to use this. And I like this because visually it's closer to what's happening with a longitudinal wave or with sound specifically. However, I don't know if I use this again. All right, we got the time. We're going to do this. We're about to step out into the hallway. I will need a volunteer. It's not like the last time where you're going to be shown to be weak. Or strong, I guess it depends on where you were standing. Let's see, and I need a bar. All right. Do I have a volunteer? All right. This. And you have a move down the back end, you can slide that through. I don't know if you slide it through immediately, but something. Yeah. Okay. All right. Roll the floor. Now just keep it out for right now, just hold that in. Right. When we get comfortable. All right, so what I'm going to do is I'm just going to send a wave down to the other end. So notice that the wave did travel down and hit his hand, and the question is, what happens when the wave hit his hand? All right, bounce back more specifically. How did it bounce back? Not exactly reflected. And part of that is that, you can't do the ideal vertical support yet. Okay, look at the wave again that bounces back. Opposite side. It inverts. Because he's holding it still right there, that is known as a fixed in. All right. So slide the rod through the end. Put that in the middle. Yeah. All right. So now I'm going to send the wave down to the other end, and look at the reflection this time. Same, you said same half?
Same path, because it doesn't, like, it's not the opposite like that, but it's still coming. Yeah.
All right, it's still a reflection, but this is an example of what's known as a free end. So a fixed end, it's going to flip over to the other side, and a free end, it'll come back on the same side when it reflects. All right, that's all I need for the rod, so take the rod out, just hold that in. So now what's going to happen is we're both going to send a wave. So I'm going to 3, 2, 1 pulse, and then when I say pulse, let's both go to about here. So 3, 2, 1 pulse. What happens when the waves match? Did everyone see that? One more time. 3, 2, 1 pulse. Yep. What happened after they added the middle? Okay, so which wave, after they separated, did they bounce off each other or did they pass through each other? It should have been passed through. Some people say it looks like they bounce off each other, but we can, in theory, show that's not the case. You go out to the same, and I'm going to go out twice as far. So 3, 2, 1, pulse. And that was a very clear demonstration of. Let's go with it, passes through. All right, so the point when they added together, they created a wave bigger than what we had done. So we were basically taking it out to here, but the combination went out farther. That is known as constructive interference. All right, one more time, just an example of constructive interference. 3, 2, 1, pulse. Now, let's do some destructive interference. So we're going to go opposite sides. Now wait a second. 3, 2, 1, pulse. Notice the middle didn't go anywhere near as wide as it did last time. Matter of fact, if we had done it perfectly, they would have canceled out and there'd be a point that doesn't move at all. Let's show that again. 3, 2, 1, pulse. So, hold your end fixed. I send a pulse down, it reflects back on the other side. So what's going to happen if I send a second pulse? Part of it will. So I send down 2 pulses. The second pulse is going to interfere with the first pulse I send. Now, if I do it right, if I send pulses down with the right frequency, we get what's known as a standing wave. Now, in the middle, in theory, if this were done perfectly, in the middle where it doesn't move, and at his hand it doesn't move, and ideally at my hand too, not moving at least nowhere near as much as the big parts. Those are called nodes. The places where it swings the widest are called antinodes. Let's get that going again. This is the second harmonic. The first harmonic is actually not as easy to produce on the floor here. Let's see how well I can do it. I'm sending pulses down, much smaller frequency. We have 1 antinode in the middle. In theory, we have 2 nodes, one at his end and theory over here. This is the first harmonic. I increase the frequency. Second harmonic, I increase the frequency some more. Let me get some stability. I might have skipped the third one. That might be before that. Anyway, the lab on Thursday, you're going to be reading this. Now notice that I can change it slightly, so I've just got a basic think about what my frequency here is in order to get my second harmonic. There we go. And now I'm going to tighten it up. Second harmonic there. My hand is actually moving at a different frequency than it was before. Tighten it up more. It's less effort on my part, other than the difference in speed of the wave. So give it a slack here, and put a pulse into it, so just have some idea of the amount of time it takes or how fast it's going. Increase the tension. What happened? Because with a transverse wave, which is what I'm producing here, how fast it travels depends upon how much force, that as this one moves, how much force is it pulling the next one. So the more tension I have, the faster it should be going. And actually, since it's traveling faster, I need to actually increase the frequency when I get to the second one. Because I don't have time to wait, I need to be able to meet it at the right time sooner. It's traveling faster. Let's see, so I've done the interference, I've done the probably covers it. So let's go back in. And people watching this video after 0 hours will be going. Thank you, Austin.
Do you have a way to trim when we were out?
Oh, do I have, I have a video of my doing this solo with the other end fixed. And years ago, I had a student who actually filmed my doing this in the hallway. I cannot find, I remember this, I think I remember the student's name. I cannot find the video.
Yeah, no, the question is now, if you don't want to pause the whole thing, it is, I don't know if it's that easy to edit and just cut out.
Oh, well, yeah, I can do that.
Okay.
So if I have two fixed ends, the simplest harmonic, and a fixed end is always going to be a node. So I have two nodes here. I have a node here. I have a node here. I have an anti-node here. This is the first harmonic. The second simplest pattern I could do, again, two fixed ends, so I know these are nodes here. That's the second harmonic, which is the easiest one to produce out in the hallway. 3 nodes, 2 antinodes. The next one. Now recognize, even though I have them drawn sort of like that, this is vibrating back and forth. And you can experience this on Thursday when you're running using the string vibrator and the string's moving back and forth. You potentially are not actually going to see it here in the middle. You'll see the two ends like this because that's the point when it stops and changes direction. But it's moving so fast here, you're not necessarily going to see it here. But if you just stick your finger there, you're going to feel the string hitting your finger. Third harmonic. And we'll throw the fourth one in there just for fun. And so these are typically the way that the harmonics are drawn. If this distance here is L, just the distance between the two ends, well, let's figure out what the wavelength would be. So how many waves is that?
Like it's half of a wave.
Yeah, it's half of a wave. Because if you think about a full wave, the full cycle for cosine or sine, it goes up, down, and then back up again. That just goes up, then down. So that's a half a wave. So my length, L, is equal to a half of a wavelength. So my wavelength is 2 times whatever the distance was. I have a full wave here. about, go up, I go down, and I come back up again, basically a cosine curve there. L is equal to the wavelength, or the wavelength is equal to L. I know that second part's shocking given this. How many waves here?
1.5.
So L is equal to 3/2 of a wavelength, or 1.5 wavelengths, or the wavelength is equal to 2/3 times L. And in the last case, how many waves?
2.
So L is equal to 2 times the wavelength, or the wavelength is half of L. Recognize every time we go to the next harmonic, we're adding a half a wave. One fixed, one free. Fixed in is a node, a free in is an antinode. The simplest one. How many waves is that? So L, at this distance from here to here, is L. This is equal to 1/4 of a wave, or the wavelength is equal to 4 times L. Now we're going to get into a little bit of a change in language here. If you watch my videos, the next simplest one is that, the fish. I have called this for years the second harmonic. Some textbooks, and possibly all textbooks, and I just got my wires crossed at some point in my life, call this the third harmonic instead of the second. That the second, they would claim the second harmonic doesn't exist. It goes from the first to the third, where the harmonic is, you're always a multiple of that. So since this is 3/4 of a wave, it's the third harmonic. I think in all my videos at this point, I still call that the second harmonic, just because it's the second one. Just be aware of some funky language for the one fixed, one free in. And eventually I will fix that in the videos, but it's not happening this semester, not gonna happen this semester. The next simplest one, again, we add a half a wave every time, and that was adding a full wave, so let's try that again. Two of those things, so start here, go down, up, and then there we go. There, finally. 1 1/4 waves, where the wavelength is equal to 4/5 of L. And what the heck, let's do the next one. Either the 4th or 7th. That's 7/4 of the wavelength. Now, 2 fixed-ins we demonstrated out in the hallway. I think people generally have a good grasp of that one. But what's an example of something with a fixed and a free in? We have several of them lying around the room here. This is an example of something with a fixed and free in. The free in this particular case is the open end of the tube, and the free end and the fixed end is the one where basically the closed end. Similar to organ pipes. You can fill this with water and you can change the length of, in essence, the tube. And so probably next Tuesday we'll go through that example. And then 2 free ends. The simplest wave. We have 1 node in the middle, 2 antinodes. How many waves is this?
One.
Nope. It is a half. If you think about this being 1 wave right here, and you basically are chopping off the 2 quarters at the end. So the math piece of it is identical to over here. Then you add a half wave every single time. That's a full wave right there. I guess the candy wrapper. The DNA spiral. Small tube animals. And the example there. And we have an example for that. And matter of fact, can use it in order to figure out what the speed of sound is, which we will. Or I guess we'll assume the speed of sound and we'll use it to predict what the frequency that we will hear. We do have enough time. I'm going to do it. I know there's only 5 minutes left and I want to hand stuff back, but yes, Jesse, you're closest. If you go around, should be a box about mid-level over there with tuning forks in it. If you could grab a tuning fork, I appreciate it. All right, so what's going to happen is I want to get water into this tube right here. So I pour it into the big reservoir. Water comes down here and it's going to start to show up over here unless there's a kink. Thank you very much. And I can see it, and you probably can't yet. So let's put it where it's a little bit more visible. And you can see water starting to come up along with a whole bunch of stuff. There we go. So this level should be rising until it gets to the same level as what's in the reservoir here. And the tuning fork, there we go. Now, whenever you're using a tuning fork, please do not bang it against something hard. If you look at some of the older ones, and this one's starting to get scratched up, they do get scratched up. So hitting something soft. Sometimes we have mallets over there with rubber stoppers, or assuming that most of you can hear that. I don't know about you, Roberto. Yeah. Okay. Your hearing's better than mine. As I put it over here, the sound waves are bouncing up against this and then coming back. Now, I've hit a harmonic when my antinode is at the entrance here, because that's when you get the biggest vibrations, and the biggest vibrations cause the biggest changes in pressure in your eardrum. So we can change that water level. Actually, let's make a prediction. This is 256 hertz. I know that the speed of the wave is equal to the frequency times the wavelength. The speed of sound is roughly 340 meters per second. And that's equal to my frequency there, which is 256 hertz, times the wavelength. Therefore, the wavelength is, someone with a calculator still out. Something.
1.33
meters. Now the first harmonic should occur, that's right, we're over here. First harmonic should occur when the length of the air column is a quarter of that. So a quarter of that.
0.33.
Oh, yeah. Now there are 2 centimeters at the top not accounted for in the device here, so we should get a little bit louder when the water level is somewhere around here. That's at the 31 centimeter mark plus the 2 centimeters, which puts it at 33 centimeters. And the tuning fork. And it got a little bit louder there. At about the 31 centimeter plus the 33 centimeter mark. Sometimes the stuff I'm teaching you actually works out. So let's end it on that note right there. Oh, let me hand stuff back to you as you